All right, I'm increasing the price of that. Fuck that shit, bro. Very funny. Very funny. Very hilarious. Spending money to end my stream. But also, that's crazy. 10,000 is too cheap a bill. It needs to be more expensive if I'm gonna lose real life money on that. That's crazy work. Never. I mean, it was funny, so I can't help but laugh. But how much is it? It's 10,000. That's too cheap. We're gonna have to add an extra zero in there, make it 100,000. Maybe that's the way we do it. Every time it hits, we increase the price. Every time it misses, we decrease the price. It's a dynamic market exchange. What can I say? All right. But with that in mind, fuck it. I'm just going to get started because I've lost 30 minutes of my time. So I'm going to end the music and I'm going to quickly go over why I'm doing this. So for those who don't know, I am a PhD chemist. What does that mean? It means that I have access to a plethora of knowledge that is generally highly gatekept, unfortunately. It's gatekept for a variety of reasons. One is it's gatekept for the sake of keeping it exclusive, which I think is one of the worst reasons. It's gatekept because there's a high bar to entry. You have to be both really good in school and you have to have a lot of experience working in, say, like a lab area, which is oftentimes not available to a lot of people. And it's even just gatekept based on like where you're born. A lot of people, like one of my old colleagues that I used to work with, she grew up in a place where there just wasn't a lot of access to chemistry equipment. And so the opportunities for getting into research were just extremely limited. And so because of that, I'm really interested in sharing that knowledge widely because one of the things I learned that was kind of sad when I was teaching as a TA was that students generally don't like chemistry. And I think that's really unfortunate because I think chemistry is actually a very fascinating subject, one that has spanned thousands of years. Dating back to like ancient Egypt, they were doing chemistry. So I'm really hoping that by sharing chemistry from a different perspective than, say, what you'd be told or taught in traditional academia, we can all come to a better understanding of both how the world works around us, but also a greater appreciation and potentially even fondness for chemistry as a whole. Because I can understand why teaching for a test is way less exciting than understanding for the sake of knowing. So, if we're going to do this, I think the best place to start is with the start of chemistry, which is atoms. So, the first question we're going to ask in this little series, I guess, of like lectures, but they're not really lectures, is what are atoms? Now, I'm hoping by the end of the stream that you will unequivocally be able to answer this question without fail. So, before I get into it, I just want to give shout out to this book. So this book, From Atomos to Atom, was a book that I was able to find free online and was a great resource for setting up a lot of this history that we're going to start with from the Greeks all the way through the Middle Ages. Once we got into the Renaissance, a lot more resources became available, and so I'll make sure to show all of those sources at the end. But if you're interested at all in any of the history and you're not a chemist, this is a great resource to check out if you really want to learn more. So, with that being said, what I want you to do is I want you to think, what do you think of when I say atom? Now, for most of you, you probably thought of this image. This is what was known as the Rutherford model, and we'll get to it in a bit. But this image is probably the most popular, shown in all sorts of media like The Simpsons and Jimmy Neutron, for example. However, I want you to think a little bit deeper. Let's go back to high school real quick. So this is you. You're in your really diverse, very marketable friend group, and in the middle of chemistry class, in between trying to think of ways to make methamphetamine, you were probably taught a couple of things about atoms. This is probably what you were taught. You were taught that there is an atom that contains a nucleus, which is made up of protons and neutrons, and this nucleus is surrounded by electrons that fill up in specific energy shells. And it's the exchange of those electrons between different atoms or sharing of them that leads to all the chemistry that happens in real life. Now, what's wrong with this model? This model is perfectly fine if all you care about is passing your high school exam. However, I think this model does a great disservice to you. It doesn't teach you anything about how atoms actually work. But furthermore, it does a great disservice to the centuries of philosophers, alchemists, alchemists, chemists, and later physicists who've spent literally their lives trying to understand what builds the world around us. And so I'm hoping that by going through this history, you'll gain insights that go way beyond what you learn in high school. And this will also feed back into the end of the presentation. So stay. That's my engagement call out. I'm trying to get you to stay. Smart. Ads? Seriously? Oh my God. Can I snooze the ads? No, it won't let me. Brother. Whatever. I'm going to wait till the ads are done. So let me know when ads are done. Because I don't want people to miss if they just happen to get ads. Wait. Let me know when ads are done, because I don't want to be an asshole about it. Let's see. I do that. There you go. Pre-roll off. Okay, so it should be done in a sec. Okay. Oh my God, I can't believe I have a subscriber. Hey, I thought I ended this joking. Fair enough. I have to do it today. I can't wait till after, because I'm trying to work on other things after the break. Specifically, I want to start the next chemistry stream. So that and some other things. So for now, we did I felt bad if I truly didn't give it some light of day. So I did at least stop for 30 minutes, because I would have felt like a huge asshole if I didn't at least adhere to it once. But next, I'm raising the price. I'm going to make it dynamic. So whenever something happens with it, if it hits, I raise the price. If it misses, I lower it. So because it hit, I'm going to add a 0. And the next time that ever gets redeemed, we'll flip it. And if it misses, then I'll take away a 0. But if it hits again, another 0 gets added. I think that's the way to go. But I'm currently stopping because there's ads for some people. So I don't want to I don't want to step on people for that reason. All right. Let me know when ads are done, just so I can tell. Just want to make sure. They should be ending in just a second, I believe. Let's see. 16, 15. Yeah, so in like 14 seconds, the ad should be done. That's good. Excuse me. All right. Okay. Ads should be done, I'm pretty sure. Let me know if I'm right. I'm pretty sure ads are done. Is that true? It says pre-roll is off. So I'm pretty sure ads are done. Okay, cool. I'm going to continue then with the rest of the thing. And just let me know if ads come up again in the future. Okay, so where we ended off, I'm hoping that by the end of this, you'll get insights that are far better than what you would have learned in high school. So let's go. Where do we start our history? We start in classical Greece. So it's like the 600s BCE. What does the Greek man ought to do? Well, you might compete in the Olympics for your city-state. You might set up an orgy with the boys, or you might do this new fancy technology called thinking and become a philosopher. Now, before we get any further, I want to make sure I set the stage for what is philosophy. Philosophy is fundamentally different from science. Scientists come up with a hypothesis and run experiments to get data that they can either use to prove, disprove, or even come up with a new hypothesis about the world around us. Philosophers operate in a different sense, where they come up with a hypothesis and they use logic and debate to try to come to what can be more true. So even though they can come to the same conclusions, the method by which they come to those conclusions is fundamentally different, and it is the mindset that we have to continue with up until the Renaissance. And so it's about 600 BCE, and suddenly philosophers start thinking, what is matter made of? And so we get a start with Thales in 600 BCE. He goes, there must be one primary matter from which everything is based, everything in the world. For some reason, he says water. I have no idea why. There's no reasoning for it. He just says it's water because fuck it, why not? And as stupid as this idea is, a lot of people run with it. So his student, Anamenses, I'm going to butcher a lot of names. He says Thales is right, but obviously it's not water, it's fucking air, of course, dumbass. But we go a bit further, 100 years later, and we get Heraclitus, and his reasoning for why fire is the primary matter is actually kind of important. He says The reason fire is the primary matter is because things change with no relation to their original identity. Think when you burn wood and it becomes different gases, you could burn oil and it would become the same gases. You would have no idea if it was oil or wood. So because you can't tell what the original substance was, the only thing that is true in reality is that things do change, and for some reason fire represents change. So that's the logic he comes up with. Now, why is this important? Well, we get an important guy, Parmenides, and he looks at Heraclitus' logic and he says that's dumb as fuck. See, Parmenides, he's a bit different. He likes to think for real. And so he says that change is an illusion. He literally states, all that is together forms the being. Being is that which must be one, for if it were manifold, there would have to be something which divides it. But outside being, nothing is. Therefore, there is nothing which can divide being, and therefore being is one. This one being is also unchangeable. For what could be the meaning of change? Basically, he's saying that there has to be fundamentally something that is true, and all that matters is that while it can change, that change itself is not real. But he doesn't know what that fundamental matter is. So this becomes a dilemma that Parmenides sets up. And so the first word, or first history of the atom, comes from Democritus looking at Parmenides' idea. See, he thinks Parmenides is probably right. There has to be something that's fundamentally true about the world. However, changes themselves are also real. So if changes are real, but there's something that is fundamental, what could that be? He says, all apparent change ultimately rests upon local motion. What is the motion of? Well, that motion is of something that is divided into a number of beings, each of which, however, is in itself unchangeable and indivisible. The word indivisible in Greek is literally atomos. That is where atom comes from. So this can be kind of weird to understand, but what he's literally saying is that atoms or atomos are some small thing that can't be broken up further. And what we see as reality is the movement of those things. But all of those small things are the same. They are fundamentally true. And so this idea catches on pretty quickly. We get Plato, who looks at, again, can't fucking pronounce these names, Empedocles. So Empedocles looks at Democritus, comes with this idea of elements, which are fire, earth, water, and air. And Plato, you literally uses math to somehow prove the earth is a cube. Again, not sure how he came to that conclusion, but fuck it. Plato was pretty smart. He was a math guy. However, as good of an idea as this is, I mean, we literally get some really, really early idea of atoms. Something's pretty wrong. See, for 400 BCE, we're pretty much there. But there's one villain that'll come into our story, and we're not going to see anything happen for hundreds of years. So, who is this guy that is our villain? See, this is Aristotle, the evil, devil-horned philosopher. See, Aristotle, he's not like the other philosophers. He's a thinker, but he's not like the other thinkers. He likes to do his experiments, and he says everything that is real can be viewed through your eyes and your senses. So if you can sense it, it's real, and anything that's just from the brain, bullshit. So Aristotle, being the sensible thinker that he is, hates Parmenides' dilemma because it's not based in reality. It's based solely in thought experiment. So he thinks Parmenides' dilemma is fundamentally wrong, and he comes up with his own proof for why it's wrong. However, he then takes a look at Democritus, and honestly, he doesn't actually have much issue with it. What he takes issue with is the idea that you could come up with this logic and somehow use that to define reality. However, he doesn't actually have any issue with the atomos itself. And in fact, he would come up with his own idea of the smallest part called the natural minima. The natural minima is basically just a simple thought experiment where if you took some meat and you extracted all of the water out of it, then you took some water and extracted the meat out of that, and you keep going in a circle, eventually there will come to some natural minimum where you can no longer extract out of that. And from this, he'll come up with a number of sensible things like elements that he calls fire, earth, water, air, all based in touch. He comes with all these stupid ideas. Now, why does this make Aristotle a villain? Well, the church loves Aristotle. See, they loved him because his philosophy was smart enough to be loved by the people, the common folk, but it was dumb enough to explain everything the church needed to explain. For example, it could explain why Moses parted the water. It could even explain why priests like to touch kids. Either way, this would set a precedent of the church would set a precedent where you could not challenge any Aristotelian ideas. So it would be a long, long, long time before we would see anything. And so we're starting to go through history. We get the fall of Rome. Everything goes to shit. We then get a lot of wars that Europeans like to call their culture for some reason. And then there's a Black Plague. Everyone dies. Oh no, sucks. But then we finally hit the Renaissance. And so once we hit the Renaissance, we finally get back to thinking again. But I want to keep in mind, this has been over 1,000 years now. It has been a long time. So going into the Renaissance, Plato is finally rediscovered. And Plato, while he does disagree with Aristotle, his ideas originally were sort of heresy. You couldn't accept them. But now his ideas of using mathematics to explain the world around us is great. Everyone starts to love it. And so this is the world that would help create some of the great minds that would go on to inspire the work we see. So we get people like Da Vinci, Copernicus, Galileo. All these guys were very important for transitioning from that Aristotelian to that Platonian / mathematical way of understanding the world. And from there, we get the goats like Newton, who would go on to develop a calculus and simple physics we use today. And then we get Huygens, who would go on to develop some of the physics great among them. He would literally come up with the wave theory of light, which is so important to today's understanding of the world. So from there, before chemistry starts to develop, we have this idea based in alchemy. And alchemists come up with this idea called the theory of two principles. Essentially, they say that all metals are made up of quicksilver and sulfur, but these aren't the quicksilver and sulfur you understand. See, the way they understand it is that sulfur kind of represents the burnt / tarnished nature of something. In principle, it is something that is bad, whereas quicksilver represents the liquid / metallic behavior of things. So it's not like elements as we know them today where they're like true things. It's more this idea of something. So to put that into practice, gold, which a lot of alchemists were really interested in transmuting, was the process for them of taking some metal and removing all the sulfur out of it to be left with a purely quicksilver compound, which was gold because it was perfectly metallic. And that's because gold does not oxidize in air. Although they didn't know that, they just knew it didn't tarnish. And so although this dogma was able to exist in Aristotelian ideas, it was already starting to be challenged. See, we get this guy who, again, do I have his name? I can't remember how to pronounce his name. Fuck, wait, I'm looking at my notes. Give me a second. Damn it, I can't. Did I not write his name? Oh, okay, there we go. Paracelsus. So we get this guy, Paracelsus, who's the guy that, he also has the name Hohenheim, which goes on to inspire a lot of alchemic media. Hohenheim here, he starts distilling things, and he finds that there is a metallic component to metals, a vapor component to metals, which is the gas he was distilling, but he sees that there's a salt that's always left over. And so for him, he comes up with the idea of three principles, which is salt, quicksilver, and sulfur. But already as we're going into the Renaissance, this idea of the principles is already starting to break down. So going forward, we get Senner. This is slide 50. So Senner was a chemist who was focused on medicine and philosophy. So I want to make it clear, this is the 1500s, 1600s. Philosophy and chemistry are still the same thing. There's no separation between science and logic. But he's kind of confused by this natural minimum of Aristotle and this atomos of Democritus. He's really trying to take both of these ideas and get them to work together with one another. Sorry, I'm trying to, I am reading chat. I'm making clear. I'm going to acknowledge a lot of stuff at the end because there's so much to get through. So I really want to go through the whole story. But I am reading chat. Yes, I started with the Greeks and I did see the Parmenides nuts 5 times. But I'm trying to go through the whole thing because it's so much. So I want to go through it and then hopefully with the time left over we can talk. But anyway, Senner is trying to take these two different dogmas, the atomos of Democritus and the natural minima of Aristotle, and he wants to combine them together, and he basically finds that they're the exact same thing. They're fundamentally the exact same concept. So then he goes in and he publishes a book in 1618 called The Summary of the Physical Sciences. And so he publishes ideas about the natural minima from a philosophical point of view. And he basically would talk about how the atom and the natural minima are the same. However, a lot of people at the time who were still philosophers who were in the Aristotelian dogma do not care about this book. They just don't give a fuck. So he then, a year later, publishes The Point of Agreement and Disagreement Between the Chemists and the Followers of Aristotle and Galen in 1619. And he says, quote, chemical composition is the motion of the minima towards mutual contact so that the union is affected. However, he thinks Democritus was wrong about atoms. See, Democritus believed that all atoms in nature were the same. The only thing that mattered was the motion of them. That's what made everything different. But Senner, based on his work as a chemist making medicines, he says, hey, in order for chemistry to make sense, there has to be some differences between natural minima. Otherwise, why wouldn't you be able to turn everything into the same thing? And so he's a little confused by this. So he then says this in this book. The smallest particles are called minima of nature, atoms, and indivisible corpuscles of bodies. They owe their names to these facts that they cannot be further divided through natural processes and reversibly form the building blocks of all natural bodies. They are, however, so small that they escape detection by any sense experience. Atoms are not all of one kind, but they are several kinds in accordance with the diversity of the natural bodies. Therefore, we ought to consider separately the atoms of simple bodies, which are called elements, and those of compound bodies. Senner in the 1600s comes up with the first idea of the element. Not element as in a principle that defines all of nature, but element as something that is real and indivisible, something that is true and fundamental. And so, there's still two problems with this, however, unfortunately. Is this slide? The fuck? Okay, sorry. I'm looking at my notes. The two problems are this. First, was an atom of a pure element, was that the same form of an atom in a compound? Basically, I'm just going to use modern elements for this. If there's oxygen in water and oxygen in oxygen, are those the same type of oxygens or are they separate oxygens? That was the first question. The second question was, if compounds were made only of atoms, or were they composed of a mixture of atoms and other things? Basically, was there atoms and some other form of matter, or was there only atoms at the smallest level? And so, a few other philosophers would go on to tackle this. We get Google, who died at the ancient age of 21 years old, and he would note that the reason water evaporated was because air got in between the water particles using the atom theory. And then we get Gassendi, who's a Catholic priest, who believes that atoms are real, but he believes that everything that happens is God individually moving all these atoms. Yeah, no, he was fucking 21 and ancient, bro. Motherfucker was gray. Literally, look at the photo. Anyway, the next important figure, though, is Descartes. See, Descartes is also a philosopher, but he was inspired by mechanics, basically the way things move. And he is so narcissistic that he comes up with his own system to explain atoms in what he calls the clean manner, which is basically anything that he believes is true again. Obviously, philosophers in the past, they had no, people to actually tell them to fuck off, so they just had to choose what they decided was right and wrong. But he was very particular about everything. And so, he comes up with two ideas. First was that particles move in unison to appear as a whole. Basically, if the water is moving, all of the particles in that water are moving at the same point. And second was that in the beginning of history, all particles were separate, and what ended up happening to create different particles was basically all these particles hit and rubbed against one another to create different masses of particles, different sizes. And although that idea is kind of stupid and doesn't make sense, it's important because this is the first time that we get something like mass or some empirical thing that can be measured to understand things like atoms. This is the first time people have related the idea from atoms as a philosophical idea to something that can actually be understood. Because we can't understand the mind, but we can measure things. Humans are very good at that. And so, from there, he writes, by heat and cold, nothing else is to be understood, but respectively the acceleration and deceleration of material particles. The motion of the particles is called heat, which is greater than normal and affects our sense of touch, for the concept of heat is derived from sense experience. When bodies are moved by heat more than they can not remain in as narrow a space as they usually occupy when at rest or in less motion. Basically, this idea is true today. It's that everything is made up of particles, and what we consider heat is the motion of these particles. And so if these particles are constantly moving and hitting into one another, if they're moving really fast, the space between them has to increase. This is a true thing today that would go on to inspire later people with things like gas laws, but this is known as heat expansion. Anyway, from this we get Robert Boyle. Now, Robert Boyle is known as the father of modern chemistry. Boyle is so fucking goated because unlike everyone we've mentioned before, he was the first person who's not a philosopher. See, he still basically did philosophy, but he was a physicist who was really, really interested in understanding the world around us from a scientific and empirical perspective. And so, with his genius, he would go on to pen the skeptical chymist. Back in the day, alchemists and chemists were oftentimes the same thing, and they were called chymists. So he writes the skeptical chymist, and he would help end the stronghold that philosophy would have on atomic theory. He would directly state that the old Aristotelian theory of 4 elements was complete bullshit. He would even go on to completely disprove the idea of the theory of 2, although what became 3 principles with the idea of salt. He would define his own version of what is an element. With this, I now mean by elements as those chymists that speak plainest do by their principles, certain primitive and simple or perfectly unmingled bodies, which not being of any other body or of one another are the ingredients of all those called perfect mixed bodies or compounds, are immediately compounded and into which they are ultimately resolved. Everything in the world is made of small atoms that are perfect, and it's the mixture of those things that we call reality and matter. Robert Boyle is actually so goated. Anyway, although Boyle was goated though, he would get a couple things wrong. He believed it was literally impossible to separate atoms into pure substances. He believed everything in the world had to be a compound. He also believed it was empirically impossible to study chemistry, or atoms specifically. He thought it was literally like just an idea that we know to be true, but is unprovable, basically. And so from here, we get these 3 guys, and they would go on to define the 17th century, which is the idea of the atom had at this point transitioned from a philosophical, untestable idea to a scientific, empirical idea. And that is too important not to state. In 100 years, we completely transitioned from Democritus's theory to a real understanding of the world around us. Now, unlike the 17th century, the 18th century is kind of useless. We're going to talk about a few things, but we're going to mostly skip through it. See, in the 18th century, Newton would go on to find out gravity is real. Pretty important, I guess. He would also, again, discover calculus. Again, important. Rutherford would go on to isolate nitrogen gas for the first time. And Lavoisier, a couple years later, would go on to isolate oxygen. This was the first time that we proved that the air around us is made up of a mixture of things and is not just one uniform thing. But these people would go on to inspire Dalton. The first modern theory of the atom is going to come from John Dalton. See, John Dalton was an English physicist and chemist who would make what we consider the first modern atomic theory. And so at first he was a meteorologist and was interested in the properties of gases. So upon becoming secretary of the Manchester Library and Philosophical Society in 1800, he started running experiments on the properties of gases. He would write a series of essays where he would define so much of what we consider true about modern gas theory. So, in the first essay, he would write, the density of elastic fluids is exactly as the compressing force. All other circumstances alike. Literally saying that if you press a gas, it doesn't matter what the gas is, it'll experience the same force. Very important. He would then in the second note the equilibrium between liquids and vapors. Literally, things are always evaporating and condensing at fixed rates depending on their temperature. And he would literally measure it for so many temperatures of Fahrenheit. It's insane. He didn't use Celsius because he was a true patriot, by the way. Fucking real for that one. The third's really not that important. He basically just shows that evaporation's a process. Pretty cool. Yeah, not that useful. But in the fourth, he would come up with empirical evidence for what would later become the first gas law, which is used in so many processes today. And he would find that the gas density is directly proportional to the pressure being applied. This is an identity that the gas does not matter, just that the pressure is what matters. And so from this, he would go on to rigorously and highly documented experiments. He would even discover so much about gases called Dalton's partial pressures. That is to say that the pressures of all the individual components in the gas is equal to the total pressure of the whole gas itself. This is so important. And from all this empirical data, Dalton would go on to write a new system of chemical philosophy. In this work, he would document many properties of chemistry that are still held up today. Some of it does not, but at the time it was the standard for known chemistry. And he would write in this book, the observations have tactically led to the conclusion which seems universally adopted, that all bodies of sensible magnitude, whether liquid or solid, are constituted of a vast number of extremely small particles or atoms of matter bound together by a force of attraction. And he would go on to define what an element is. By elementary principles or simple bodies, we mean such as has not been decomposed, but are found to enter in combination with other bodies. We do not know that any one of these bodies, denominated elementary, is absolutely indecomposable, but it ought to be called simple till it can be analyzed. The principal simple bodies are distinguished by the names oxygen, hydrogen, azote or nitrogen, carbon, sulfur, phosphorus, and then all of the metals. He would literally describe what we would consider the modern theory of atoms and elements, which are so important. Furthermore, Dalton would then go on to describe methods for ascertaining the weights of different elements and compounds with respect to one another. He would define the idea of mass balance, which is so important, and would define what we later have as stoichiometry. And once Dalton's theories was introduced, things start to develop very rapidly, since there was now a known method for comparing things, relative masses of elementary substances. People's chemistry really took off. John Baraluzzi, I don't even know how you, Barazillus? Jans? Again, fake ass name. Average European name. He would develop much stricter methods for determining relative masses than Dalton, and he would start using the first letter of element Latin names to refer to them on paper, which is what we use today, using a letter to describe elements. Avogadro would go on to ponder why 1 volume of oxygen, when reacted with 1 volume of nitrogen, would make 2 volumes of nitrogen oxide, and he would go on to discover what is Avogadro's law, which is that the volume of gas is directly proportional to the number of atoms, which would go on to combine with some of Dalton's laws to create what is becoming soon the ideal gas law. And since the masses of elements were so regular and the properties of elements were so similar, masses were so similar that some chemists, like, that's not Amadeo Avogadro, that's a mistake, like Mendeleev and Mayer, they would group elements according to their masses and to their properties, and they would come up with what would become the modern, or the first versions of what would later be the modern periodic table. And since the elements were so regular and properties of elements were so specific, there was even proof that maybe atoms were made up of smaller particles. See, there came a problem where once the measurements got so good, some of the trends started to break down. So for example, iodine shared a lot of properties with things like chlorine, fluorine, and bromine, but it weighed less than tellurium, which shared properties with things like oxygen and sulfur. So by mass, the iodine should come before the tellurium. However, by chemical properties, tellurium should come before iodine because of these chemical properties. So there was already some show that it might be a different order than what we thought, and that atoms were made up of elementary particles. And so before I continue to the next part, I just want to quickly summarize everything, because we have literally gone through about 1,500 years of history and so much has happened. First, we transitioned completely from Democritus's philosophy to Dalton's science. We are no longer in the realms of logic. We are an empirically backed and studyable science. Then we were able to go from identical atoms to distinct elements, each with their own properties and weights that could be changed between one another. Then we were able to use these atoms to define things like temperature, pressure, and volume, and be able to relate them to just simple constants, which is so important. And now atoms are even potentially made of smaller particles that we cannot describe. That is how much has happened in the last 1,500 years. And so it took about 200 years from Thales to go to Democritus, and then about 1,500 years to get to center. But in that time, we have discovered so much about the fundamental world around us, and we have never even seen or proved atoms exist. So, before we go further, we need to go over electromagnetic radiation. This will be important because a lot of what would go on to discover more properties about the atom has to do with electromagnetism. So, as previously mentioned, Huygens, who I know you forgot about, by the way, he had shown previously his theory of wave nature of light. And this new guy, Leon Foucault, who I had to Google how to pronounce the name of because I knew I was going to fuck it up, he proved that lights were waved because the rate at which they move between different substances was constant. Basically, if you put light in the air and then into water, its speed would change. But then once it came out of the water into the air, its speed would be the same in both mediums. However, this sort of proposed one problem. See, if light is a wave, what was it traveling through? Just like sound waves that we hear all the time, that's just a compression and decompression of air. Or waves in water is literally the movement of water. So if light is a wave, it has to be the movement of something. And so there would become many ideas of what people would call ether, or some unimaginable body that somehow light was able to travel through. And these theories could never really hold up, and that's because it was complete bullshit. See, Max Planck would go on to prove that light is actually just the oscillation of electromagnetic radiation. There would be a magnetic field and an electric field that would oscillate between one another, and the total direction of that is what we consider light. And so this was very important. We could use this to show that things like microwaves and visible light and X-rays and ultraviolet were actually all the same thing, just different forms of electromagnetic radiation. It was previously assumed that these were all completely separate things. Also in the 19th century, from the work of Michael Faraday and then later Arrhenius, we would prove the existence of ions, which, I'm not going to lie, when I was doing this research, I didn't even think that ions had to be proved, because they're so ubiquitous in chemistry nowadays that I was just like, oh, ions exist. But it took a long time for people to even prove that ions were a real thing. But in the 19th century, the combined work of these two people would show that elements could differ from one another only in their charge, not in their mass or elemental composition. And so the thinking was that because atoms are particles, the only thing that could be causing a change in electrical charge and not a change in element had to be some particle that has some intrinsic electrical charge. This was the first idea of the electron. This idea would later be confirmed by J.J. Thomson, who in 1897 would go on to show that the previously described cathode rays were made up of electrically charged particles. He literally wrote, "The experiments discussed in this paper were undertaken in the hope of gaining some information as to the nature of cathode rays. They are in fact wholly material, and they mark the path of particles of matter with charged negative electricity." This would lead Thomson to come up with what he believed were atoms. He believed in what we call the plum pudding model, which is basically that there's some pudding of a positive charge filled with some plums that are electrically charged. In this case, electrons, although he actually hated the name electron, weirdly enough. But basically, there was already this understanding that the atom was made of other things before we even hit the 1900s. And so from there, this would quickly be destroyed in the 20th century. See, in the 20th century, we would get Ernest Rutherford. So Ernest Rutherford had been working on alpha and beta radiation for a long time. Sorry. So alpha radiation is just the movement of helium particles of high energy, and beta radiation is the movement of electrons. So he had been working on this in the late 1800s, early 1900s. And so he would work with Hans Geiger in 1882, or not 1882, in 1909, and he would conduct an experiment where he shot alpha particles at thin gold foil. If the plum pudding model was real, the alpha particles should be able to go straight through the gold foil without any issue. However, when they actually shot the alpha particles, these particles kept getting deflected in all sorts of directions. And so this proved that the positive charge inside the plum pudding model was incorrect. The charge had to be localized in order to divert the flow of the alpha particles. And so, from this in 1911, he would come up with his own idea of the atom, which was based on what he called a proton, or something of positive charge. See, the deductions from the theory so far considered are not independent of the sign of the central charge, and it has not been so far found possible to obtain definite evidence that determine whether it be positive or negative. However, the effect of radiation in reducing the velocity of the beta particle should be far more marked with a positive than with a negative center. So he had proved the existence of a proton, and we had previously shown the existence of the electron, so now the atom had to be with a proton with electrons surrounding it. This is what would become the Rutherford atom, which I showed you earlier. So, however, he would even go on to describe an idea of some other particle inside, which would later become the neutron, because the masses of elements didn't correlate with the masses of protons. So he had already had some idea of some neutrally charged particle, although he would never prove this, unfortunately. However, this model had some issues. See, it couldn't explain what was at the time known as the emission spectrum. See, what ends up happening is when you have some element, in this case a hot gas of some sort, and you heat it up or you use electricity to excite it, it shoots out very, very specific wavelengths of light. If atoms were just protons surrounded by electrons at random distances, why would it make light? That makes no sense. So there had to be some reason it makes very specific light waves. And so this would come from Niels Bohr, who would go on a few years later in 1913, so literally 2 years later, he would publish his model of the atom. It was based on Rutherford's experiments and the known emission spectra of hydrogen, and he made what is known as the planetary model. In this model, electrons would move around the proton in very specific orbits. They would orbit the proton, and it was the movement between orbits, so from, say, electron in the first orbit to the second orbit, and then back down, that light would get released, and this light is what we called the emission spectrum. And so from this, we get the first time we would have any quantum in any atoms. See, because these orbitals were specific, they were discrete. So they were quantized. That's where the word quantum comes from quantized. So these quantum orbits were described by some number called the principal quantum number. And that basically indicated the atom size or energy. So the principal quantum number is the energy of the orbit. That's important for when we get into more quantum mechanical models later. So even though this model had a lot going for it, it still couldn't explain anything. See, because we knew from Max Planck that light was electromagnetic radiation, and we knew electrons were particles of electricity, Peter Zeeman proved that if you put atoms in an extremely strong magnetic field, and then you excited them, their emission spectra would split. It would get fucked up. And so, unfortunately, the Bohr model as it was could not explain this phenomena. However, Arnold Sommerfeld would go on to use this random guy's theories of relativity. Pretty brief history, I can't go over every individual person. He would show that if you understand how things orbit around things, if you have non-circular orbits, it would allow for this to work. And so that's became what was at the point the Bohr-Sommerfeld model in 1919, where we have a planetary model, aka like the sun with the Earth orbiting it and the Saturn and all those. But those orbits were not perfectly circular. A lot of them were elliptical. And anything that goes on, Arnold Sommerfeld would then use two new quantum numbers called the azimuthal quantum number, which describe the angular momentum of the orbit. Basically, that's how you got the different shapes. And then the magnetic quantum number, which was literally just how the light changed in a magnet. That was it. Basically, if the light changed upward towards the magnet, it got a positive. If the light changed downward, it got a negative. If it didn't change, it got a 0. So that's the two new quantum numbers that we get. However, this is completely bullshit. This could not work in reality. But basically, the reason this couldn't work is because it's a planetary model, everything we've described is flat. So in order for everything to work that we've described, these atoms have to always, at all times in space, be the exact same flat orientation. If you rotate it even slightly, all of that math breaks the fuck down. That is why people are like, oh, this doesn't work. It's complete bullshit. However, this would quickly be resolved by our transition from classical quantum mechanics to modern quantum mechanics with Erwin Schrödinger, who apparently was a pedophile. Didn't know this until I did research, but he was described as having a Lolita complex. Crazy. Anyway, he would just write a paper, The Quantization as an Eigenvalue Problem, and in this paper, he would derive what is now known today as the Schrödinger equation. But I want to quickly read this because it's important. In this communication, I would like first to show in the simplest case of the non-relativistic and unperturbed hydrogen atom that the usual prescription for quantization can be substituted by another requirement in which no word about integer numbers occurs anymore. Rather, the integerness or the quantization emerges in the same natural way as, for example, the quantization of the number of knots of a vibrating string. The new interpretation is generalizable and touches, as I believe, the very deeply true essence of the quantization prescription. He would go on to, in this paper, show the Schrödinger equation, which is so important to modern quantum mechanics. Basically, solving the Schrödinger equation for specific systems gives you anything that is true in quantum mechanics. And if you applied this to hydrogen, you could get what would later be described as orbitals. Orbitals are now new ways of describing the orbits in atoms. Rather an electron particle going around the proton like a planet, it is now an electron wave that vibrates around the atom or around the protons. So it can be kind of hard to understand, but if you look at these heat maps, rather than thinking of it as a shape, I'd rather you think of it as like a probability. The more white it is the higher the probability the electron is there. The more blue it is the lower the probability. And that's because these are waves, so you can't pick a specific spot. That's kind of why it works this way. But because of this, we get, again, the principal quantum number, which describes the energy level of the orbital. We get the azimuthal quantum number, which again describes the angular momentum, but this time rather than showing the shape of a true orbit, it's the shape of a probability, which you can see here. And then again, we would get the magnetic quantum number, which just shows how these orbits are aligned along a Cartesian coordinate, and that's how you get those difference in magnetic moments. These orbitals, are almost complete. However, we're missing one major addition, which would come from Pauli, who would postulate the Pauli exclusion principle. The principle states that electrons cannot inhabit the same quantum state. Basically, if an electron's already in a same, has an n equals 1, L equals 0, and an m sub L equals 0, there cannot be another electron with the exact same numbers. However, it was already known, like helium, for example, helium has two electrons. However, it only has one orbital. So if there's only one orbital, which has n equals 1, L equals 0, M sub L equals 0, but there's two electrons, there has to be one more number that we don't know yet that separates those two electrons. And this would sorry. there had to be two values for this one number because there could only be two electrons. If we saw more electrons, like 3, it'd have to be a three valued quantum number. But because there's only two electrons, it has to be two valued. It's one for each electron. And so in 1927, based on the previously known Stern-Garlick experiment from years prior, where silver particle beams split based on an external magnetic field, he would formulate the idea of electron spin, which described the intrinsic angular momentum of an electron. And this intrinsic angular momentum could only point in one of two ways, up or down. This was the last quantum number that was needed in order to prove the true orbital that we use today. And in the same year, this would be proved by Jan Bellamy Taylor, who showed the same behavior with the hydrogen atom. So even though we were focused on silver, which has a shit ton of electrons, hydrogen only has one electron, and yet its beams still split. Therefore, there's something about the electrons that is different. It's not the silver specifically. And so we have almost come up with the modern version of the atom. However, we're missing one thing, which is the neutron, which again, completely know you zoned out and forgot about it. Basically, we had to prove that the neutron existed. And this would come from James Chadwick, who literally published a paper, The Existence of the Neutron. It was shown by Bruth and Becker that some light experiments, when bombarded by alpha particles or polonium, emit radiations which appear to be of the gamma ray type. However, he would show that this is in fact coming from a neutrally charged particle with the same mass of the proton. And from this, we have now completed our model of the atom. I can somewhat decently say that this is an accurate modern depiction of the atom. And there are still things that are being probed to this day. For example, what is the shape of the nucleus? That's an ongoing research. Or what is the fundamental thing that makes up protons and neutrons? For example, we know protons are made up now of subatomic particles, further subatomic. And these somehow give protons the properties they have. So there's research going on into that today. However, I just want to recap the current timeline of the atomic theory completely. So the atomic theory started with an idea by Democritus, which was trying to understand the limits to the divisibility of matter. He concludes that all matter is made of the same particles that move in space to make different things. Later, Boyle showed that these particles are different, but they are able to describe phenomena like heat and pressure and form mixed compounds. So we've already transitioned completely from there. Then we get J.J. Thomson, who proves that electrons are real, and in order for electrons to be stuck inside the atom, there had to be some positive charges, so he comes up with the plum pudding model, where there's just a sea of positive charges filled with electrons. A few years later, we would get Ernest Rutherford, who would prove the existence of a proton, and then 2 years later, Niels Bohr would use Rutherford's experiments along with emission spectrum to come up with the planetary model, where there's shells that surround the proton that the electrons inhabit. And lastly, with the invention of modern quantum mechanics by Erwin Schrödinger, we come up with this idea that electrons are no longer true particles, but they are wave particles that have a probability of existing in very specific spaces around the nucleus. And that nucleus was composed of protons and neutrons based on experiments. And so, what's the point of all this, right? I taught you about atoms in the course of 50 minutes so far? And why should you care at all? Well, I did this to highlight that what over 2,000 years ago only existed as a thought experiment survived long enough to be proven real. The impressive part about atoms is not that they're real. It doesn't matter. What's more impressive is that we came to know they exist through a very specific and long-winded journey. It was the journey that we got to get there that was more important, from philosophy to crude experiments to precision measurement to now mathematics that predict intuition than you ever could. And so the atom you were taught in high school was a bunch of labeled balls that you memorized for a test. However, I'm going to quickly switch my camera to this. And say, I still need my newts. True atoms are a record of human curiosity. They're a reminder that theories can in fact be true. In an age of anti-intellectualism, where the fucking government is always constantly saying it's just a theory or that's not provable, that is bullshit. We can choose theories that are based in reality and are completely true. When I said at the beginning of this stream that you'll come to understand what everything is made of, I didn't just mean protons and neutrons. I meant ideas, arguments, experiments, and mistakes. Everything in the world is made of atoms. The air, the stars, the device you're literally watching this on. But our understanding of atoms is made by people. People who thought, who were wrong, and who didn't give up and completely sought the truth. And atoms are not just the smallest units of matter, but one of the biggest achievements in human history. And I'm hoping that today I've opened your mind to something that you previously didn't understand. Thank you. I mean, I feel like I should have some catchy ending to that, but like, no, thank you, genuinely. I've always wanted to talk about this. And so, quickly before I talk a bit longer, I just want to show, these are all the references I used for making this. All of them are completely available online if you need. And I wanted to make sure that it kind of reads in order based on the history or the chronology of the slides. So we have that book in the beginning, but then the essays of Dalton, and then further on. And I did use Wikipedia to some extent whenever I couldn't find ways to fill in the gaps. However, I do think Wikipedia is a semi-decent source. Again, I really appreciate you watching. Thank you. Genuinely appreciate it. Oh, my throat is sore from speaking for so long. Whew. Let me actually reply to comments because I got fucking 1,000 of them. Let's see. God, these comments are so brain dead. Betas can never understand. I've barely paid attention, but you remind me of one of my teachers I've had, one of the few good ones. I really appreciate that. I really hope the people that watch enjoyed. I put a lot of effort into trying to make this as good as possible and as understandable as possible while also trying to make it somewhat funny. I thought I originally had more jokes in it, but I thought it would be kind of annoying if it was just jokes and not real. I understand that not everyone's that interested in chemistry, but I find it really annoying when, like, content creators, I guess, they make science content too funny and not based enough in reality, because I feel like it's very demeaning to the viewer. I don't think anyone is dumb enough to the point where they can't understand atoms or chemistry. It is the world around us. And if you say someone's too stupid to understand chemistry, you're saying they're too stupid to understand reality. Like, that's a very negative and I think untrue way of viewing the world. Whew. Oh God, my throat is sore. Hoda foreshadowing again. This is all based in One Piece. W. Boyle, didn't Mendeleev make the exact periodic table we have today? No, Mendeleev did not make the exact periodic table today. He got a number of trends right, but one, not all of the elements were just known during Mendeleev's time. I can even go back and show the periodic table he had. But because they didn't have the understanding of electron configuration that came from orbitals, the way it was designed was just fundamentally different. So if I go back to that slide, give me a second. You're right here. Okay. I go there and then just do overlay. You can see that he defined groups and he got some of them right? He put hydrogen, lithium, sodium, potassium in the same group, which is right. But he also put in the same group copper, rhodium, silver, cesium. Cesium is right. It actually does belong in that group, but like copper, rhodium, and silver are gold. No, that's silver. And gold is actually in the same group. They do not belong in the same group. Nitrogen, vanadium, phosphorus, arsenic. So nitrogen, phosphorus, arsenic, and antimony all in the right group. However, vanadium and niobium and tantalum and bismuth are in a different group. So he got a lot of things right, but it wasn't exact. So that's another case of a lot of good ideas that were started at the beginning of history or before when they at the start, and rather than just being 100% wrong necessarily, the ideas were revised later on. Another good example of ideas being visited later to be revised is Newton. Newton came up with the idea of gravity and the mechanics we have today, which defined a lot of space-time physics. And it wasn't until later Einstein shows, wait, Newton's understanding of physics and gravity and the world around us isn't wrong necessarily, but it's not 100% right. And so he does more to try to amend that later. And that's where we get relativity. But Newton wasn't 100% wrong. He just didn't know the things that Einstein knew. When is a part 2 of your chemistry streams? That's a good question. I want to do a part 2. I have some ideas for what it could be. I'm also considering, so I have another idea of doing another thing like this, where it's a history. I also think it would potentially be interesting to go through some more fundamental properties of chemistry, and I could do things like demos on my desk, obviously. I can't do like demos that are super dangerous, but I could do things like acid-base chemistry and do some acid-base chemistry at my desk and describe the properties of acids and bases. So I haven't decided what I will do, but either way, I will continue to talk about chemistry. Like I said, I'm very fortunate to have access to the knowledge I have. It would be a great disservice if I didn't share it. Even if only one person gives a fuck, I'd rather one person listen than me just keep it all to myself and gatekeep it. One of the worst problems in academia is the gatekeeping of knowledge. It is extremely harmful, and it is one of the main things that has led to the environment today where there's a lot of anti-intellectual sentiment. It makes me very sad. However, I also think that is improving. I think a good example of improvement is Milo Rossi, who goes by Mini Minuteman. He's a PhD archaeologist who also makes content about paleo archaeology and tries to dispel a lot of myths about history and stuff. So we're headed in the right direction overall, but I think the more people who have the ability to admit where they're both wrong, but also the knowledge to share what's right is important for society as a whole, but science just specifically. I think it would be really sad if we just don't have any more chemists, you know? But that's where I'm at. Whew. Oh my God. See, is there anything else in here I haven't answered? Yeah, I started with that. Legit, Horton, here's a who. Bruh. Crazy. Nucleus is the powerhouse of the cell. Different nucleus, but yeah. Type shit. Add, yeah. No, I really appreciate y'all listening in, though. It means a lot to me. Genuinely. Oh, I realize I'm still on the, what is an atom? We did. The atom is a nucleus comprised of protons and neutrons, which is surrounded by probability densities of electrons. That is what an atom is. I mean, I have my little drawing there, Schrodinger. Let me try to block out the light. So that's my little drawing of it. I could also even pull out my physical chemistry textbook. Let's see. Do they have a better drawing of atoms? I don't know. Maybe the atoms were the friends we made along the way type shit. Let's see. Hey, Page 303. That's right. I used to use this book in class, actually. Like, this is a book that I used to actually use to understand things. So, like, yeah, here we go. I don't know if you can see that well, but you see, like, that sphere? That is the probability of an electron being found in a specific orbital. You can see it changes as you get farther away from the center of the atom. So that's what atoms are. They're wave equations, basically. Or at least the hydrogenic atom. Oh, let me put that back. But I do want to highlight that atoms are more than just chemistry. They are human creativity and continuity and history. It's literally culture. I mean, one of the things that I find very annoying, I heard this from my grandma once and it always pissed me off, was she said math is just a technology. And like, while that's true, math is a technology, it does a great disservice to the culture that math creates. Math is in itself a language that literally bridges language barriers. It's pure logic that can stand the test of time. It's not just a technology, and by calling it just a technology, you degrade so much of human history. Atom is the same way. If you call an atom just, oh, it's just what things are made of, it degrades so much human history and culture. And that's why I wanted to make this, to call attention to that degradation. Whew. Okay. Oh, is it? Oh, ads are running? God damn it. Snooze the ads. There we go. Okay, how long did that take? Been an hour? That's not bad. Well done, thank you. I forgot I have a subscriber, so I'm not alone when I'm just doing ads. Thank you very much. I appreciate it. I'm very proud of this. I've literally been working on it for about a month now. Originally, it was a much smaller scale, where I literally just only focused on that book and trying to use that. But the more and more I read it, the more I was like, this can be more. You know, I wanted to do it right. And so that's why I put in the work. But it kept extending the deadline a bit. And I was like, no, I need to get it done. There's a saying Hank Green has, which I think is very good. It's basically, you should try to get something 80% of the way there. If you go for 100%, you'll never be perfect. But if you go for 80% of what you want, you've done a good job. It's a good amount of condensed information that also didn't feel like it was too much. Thank you. I had a lot more in the later parts originally, so I had more in the worlds of quantum and stuff, but I truly believe quantum mechanics could be its own stream. It's that in depth, and so I thought, rather than focus on that here, just provide the bare minimum needed to understand how things changed and then move on. Because honestly, like I said, although I taught you about atoms, this wasn't about atoms, it was about the human history involved. That's why I'm much more focused on that. So it definitely could use improvements, and I'll go back and watch the VOD later, this like style of content, but I do want to share the information I have in a way that I think is enjoyable, but also not overwhelming and not degrading. Ugh. Okay. Let's see. Do I raid some today, or do I just kind of end it for the holidays? That's the real question. I need to get out of this fucking suit. It's so hot in here. Like, I'm actually burning to death. Ugh. Do I raid someone? Do I even want to raid someone? Like, who's streaming? Yeah, I'm gonna be done in a sec. Let's You know, Miss Alacion is streaming. I'll raid her. All right, chat. Okay, so here's the question. I'm gonna turn this into a YouTube video anyway. Do I do a YouTuber outro? Or do I just be normal and record one later? YouTube outro? Okay, I can do YouTube outro. What do I even say? Thanks for watching, guys. Make sure you like and subscribe. Nah, can't do that. Can't do that. Quick Spelunky to end the day badly. What time is it? Okay, you know what? Not Spelunky, but we'll do one level of Mega Man. I've been playing Mega Man 11, and I enjoy it a lot. I will do one Mega Man 11. Wait, here we go. God. Bruh. Why is my controller not working? Brother, controller lock in. There we go. Okay. Chat, pick a level. You got these 3 to pick from. Impact Man, Acid Man, or Bounce Man. This will be the level to end stream. Bounce Man? Bet. Let's do it. This will be... We'll see how quickly I die or how quickly I live. Gear 4th. Luffy's the GOAT, bro. I love Luffy so much. Although, Gear 5th is so much more goated than Gear 4th. I'm not gonna lie. I liked Gear 4th, but I remember being kind of like... I don't know, Gear 2nd and 3rd were so much cooler than Gear 4th in my mind, and then Gear 5th was just, like, awesome. Oh, Zoro the GOAT? Zoro is like... I do not understand why he's so popular, bro. I don't understand it. Not because Zoro's bad, necessarily, but he's, like, the most boring of the Straw Hats. He's, like, the only one without any development to his story outside of, like... His biggest feat is nothing happened. Literally, that's like the one thing that he has going for him. Nothing happened. Outside of that, like, what else? He's powerful for the sake of being the strongest. Like, literally, the reason he's the most powerful Straw Hat outside of Luffy is because he's Japanese, bro. In the same way that Oda made Odin, who happens to have the exact same name and happens to come from Japan, be somehow the most important person in the entire universe. That's Zoro. Motherfucker. Oh, shit. Okay. We got it. Come on. Okay. Nepotism, literally, bro. Fucking Nepo baby. Isn't he literally a king, too? Oh, you bastard. There you go. God. King of Hell type shit. I still don't like Zoro, even if he's the King of Hell. Like, that doesn't change my complaint. There you go. Got up here. Bet. Oh, I thought I dodged that. I'm so dog shit. God, this level is so hard. Not because it's actually that difficult, but because of all the bouncing, man. Like, what? Get down here. There you go. Okay. That didn't work. How do you want me to respond to that, truly? Like, bounce on it type shit? Like, what do you want me to say here? Truthfully. Yeah. Okay, cool. That guy got fucked. There you go. Let's see. Let me get that. Oh, this is the level where that motherfucker's here. I knew it. Bastard. Come on. Where's that fat ass? Fuck you. I knew... Come back. Very easy. But... Oh. Oh my god, I thought I cooked myself. Oh. What? Okay. Do I have an energy canister? I do not. Okay. You son of a gun. Okay. Whatever. We have multiple laps. That's... Fuck that guy, though. Come on. I realize I'm not really commentating much, but, you know, fuck it. There you go. Got him there. Bet. Okay, I've never gotten this far in the level. You bastard! Okay. Okay, him. That. I used to play a lot of Mega Man when I was growing up as a kid, because my dad told me how much he liked the game. So then I was like, oh, I should try it out. Oh, fuck, this is a bad spot to be in. This is not ideal. Where am I? Wait, I can just do that. Perfect. Come on. There we go. Got that one. But on Xbox, they had a game, Mega Man 9, which I remember thinking was an old game. I only found out later that it was a, like, I guess for the time it was a new game. Where they were basically trying to return to the classic style of Mega Man. But, so I played a lot of that growing up as a kid. So I always really liked this style of, like, kind of hard, but, like, very rewarding platformer. Oh, fuck me. Now I gotta figure out how to platform here, though. Can't figure it out. What do I do? That. You bastard. How the fuck do I do this? Okay. Okay. My platforming is kind of dog shit, I'm not gonna lie. I'm looking like a game journalist at the moment. There we go. Finally. Okay, here's the boss. Oh, come on. Oh, it's the same fucker from before. Got him. Okay. What's next? More level. I gotta go, like, here. Okay. Let's see him. Gets me over to the left, I'm assuming. There we go. Oh, I have to use the bathroom so bad. Oh, you bastard. Oh, you dumb... Okay. Get you to the left. Not that one. Okay, I'm up here now. How much farther till the end of the level? Kind of shocked by how long this one's been going on. Okay, I have to fall down here, but I have to keep going up for sure. Keep going this way. And now we drop down here. Oh. Okay. Just gotta go this way. Okay. Okay, this is the final boss here. Now we have to figure out what this guy's weakness is. I'm gonna try the block guy. I feel like that's the weakness. Maybe. I could be completely wrong. What the fuck is this thing?
I bet you can't bounce like this.
Oh, you bastard. What? Oh, you... Okay, I don't think that was its weakness. So... How many lives do I have left? This is the last one. It wasn't that. I don't think it's the... Is it the torch? Probably not. I don't think it is. There's no way. Huh?
Let's get hopping.
No, it's not that. This is Mega Man 11. It's not that one. Probably just try that. No, it's not that. It's not gonna be that because that one's wall based. Oh, what the hell is it doing here? Fucking Christ. Oh, oh, no, you son of a... Fuck. Well, that is a very unfortunate spot to die at. Fuck. Really? I had 2 health remaining too. Shit. Yeah, I don't think I have its weakness. Well, GG. We got 1 game in before we ended the stream. So it's 8:53 now. How long was that? I don't think that was too long. GG, bro. I'm so upset by that though. Like, come on, really? Really? I was so close. GG, bro. Alright, chat. I'm gonna now do the fucking YouTuber outro, just so I don't have to record one later. No, I can't. I can't. It's so cringe. I can't. It's so cringe to do it live, bro. It's so cringe. Like, I haven't done it live because it's just so cringe. I'm gonna do it because it makes it easier. It also makes it more coherent. Alright, chat. I'm gonna start up the raid, and as it's going out, I'm gonna do it. Start raid. Perfect. Alright. Thank you so much for watching. I really appreciate it. And I hope you all have a happy holidays. Goodbye. There you go. Shitty ass YouTube outro. That works. Get me out of here. I can't.